Hello everyone, welcome to this lecture. So, the plan for this lecture is as follows. So, now we will start our discussion on multi-party computation, how to design protocols for performing secure computation, and in this lecture we will do a warm up. We will see a very simple function, namely that of secure addition. We will see the problem definition, what exactly we mean by secure addition, and we will see a very simple MPC protocol for securely computing the addition function. So, here is the definition of the addition function, which I also call as the sum function. So, you are given set of n parties, right, P1, P2, Pi, Pn, and each party has a private bit. Okay. So, party 1 has the bit P1, party P2 has the bit B2, ith party has the bit Bi, nth party has the bit Bn, and they are private, but everyone knows that the input of every party is either 0 or 1. That is a public information, but what exactly is the value of the bit, that is not known. And the goal is to compute the addition of the n bits. So, okay. So, let us denote the sum as S. So, the final parties want to learn the sum of the n bit values, that is a goal here. And if you are wondering what is a big deal, why can't every party just announce that this is my bit and then we let everyone takes the sum of the announced bits. Well, to make the problem interesting, since we want to do secure computation, the requirement here is that we want to learn the sum, and in the process it should be ensured that no party Pi should learn anything beyond what it can learn from the sum and its own input. That means, what I want here is to ensure the following: the sum S will be finally learned by everyone. Now, P1, it will have its bit B1 and it will learn the final sum S. From that it can infer something regarding the inputs of the remaining parties, only that much should be inferred in the whole protocol. Similarly, if I consider B2, P2, it will have its own bit and it will learn the final sum. Based on that, it will have some knowledge about the inputs of the remaining parties, that is allowed. Other than that, nothing additional should be revealed, and so on. That is the goal. So, now that simple protocol where all the parties just announce their bits in public and then you take your sum is not going to work, because you are not only learning the sum, you are learning every other party's input bit, which is not supposed to be learned. Okay. So, now let us try to understand what exactly it means by saying that Pi should not learn anything beyond the final result and its own input. What does it mean, does not learn anything beyond? So, let me propose an ideal solution. This is an hypothetical solution, that means there are problems with this solution, but assume this, but let us consider this solution and try to understand that what is the information a party learns in this ideal solution. In this ideal solution, we assume that we have what we call as a trusted third party, TTP. That means it is a party different from these n parties, and it is trusted in the sense it is assumed that he is the friend of all the n parties. Friend in the sense that he is willing to help the n parties compute the sum, but even if he learns the input of the respective parties, he is trusted, he will not be leaking those input values to the other parties. That is a guarantee, that is the assumption, that is what we mean by a trusted entity, equivalent to a god, you can imagine. So, assume that such a trusted party is present, and imagine that there is a mechanism for each party to privately communicate with this trusted third party. That means, there is some dedicated channel between every party and this trusted third party. Then what will be the mechanism to securely compute the sum function? Well, the simple protocol will be every party individually communicate its private input to this trusted third party, and this communication is happening over the private channel which is available between each party and the trusted third party. That means, when B1 is communicated from P1 to this trusted third party, no other party can make out what is the bit, what is the value of B1 that is communicated, and so on. That is the assumption here. Now, once this trusted third party learns all the n input bits, it can itself compute the sum because it has got all the n input bits, and then it simply announces the result to everyone publicly. That is the ideal solution. And why it is called ideal solution? Because this is the most secure protocol that you can think of. In this process, what is the information any party learns about other party's input? Nothing. There is only one communication happening between every party and the TTP. The party sends the input, gets back the output, that is all. If I consider, say for instance, party P2, will it learn anything about B1, B2, BI, BN when they are communicating to the TTP? The answer is no, because that communication is happening over secure channels, and anyhow S is learned by everyone. So, this is the most secure solution that you can think of for computing the sum function, and in this protocol it is indeed ensured that each party, if you consider each individual party, it just has finally its own input and the sum value. From that, whatever they can infer regarding other parties input, they can make some hypothesis, okay, it could be the case that the inputs of this combination of parties is that blah blah blah. All these things are finally anyhow allowed to be revealed. We cannot prevent that from getting revealed from the sum and the individual inputs. But since no communication is happening among the parties here in this ideal solution, right, that is important. No communication is happening among the parties in this solution. Individually, a party is not allowed to learn anything in this ideal solution, right. But the problem with this ideal solution is that it creates what we call as single point of failure, namely how suddenly we will get someone who is %% trusted. This whole solution works under the assumption that there is a third party, a friend party who is trusted by everyone. How in this real world you can find someone who is indeed %% trusted? Because trust is very rare and volatile, and if there is trust in the world, then we do not need to design, we do not need to study MPC, okay. Because if a trusted third party is there, then whoever are the set of n mutually distrusting parties, they can take the help of this trusted party to keep the privacy of their messages inputs, and at the same time perform computation on their inputs. But at the first place, we are actually trying to design a protocol because we know that there is no one called a trusted third party in this real world, because there is always a distrust in the world, because without darkness one cannot know light, without hatred one cannot feel love, without war one cannot realize the price of peace, without noise one cannot appreciate serenity, and without distrust one cannot value trust, right. So, the ideal solution that we have proposed, that is why that is a hypothetical solution that will work only under the assumption that you have someone who is trusted by everyone. So, now it looks like we are kind of stuck. We do not have any trusted third party, we just have the n parties, that is all. And at the same time we want a mechanism which allows those n parties to maintain the privacy of their respective bits, but at the same time the sum should be computed and announced publicly. Looks like an impossible task, because how can it be possible that without knowing all, without anyone knowing all the individual bits B1, B2, Bn, the sum is computed, because if at all the sum needs to be computed, the n bits, the values of the n bits have to be known. Who should know that? Because we cannot afford to let P1 learn all the n bits, compute the sum and announce, or we cannot let P2 know all the n bits, compute the sum and announce, because our goal is that no single party should learn anything additional beyond its own input bit and the final sum. So, you might be now wondering that do we indeed require a trusted third party to compute this very simple sum function. We are talking about the real world MPC motivation examples that we talked about. They are very complex functions, privacy preserving data mining, checking whether there is a probability of two satellites colliding and so on. Forget about those complex functions, we are just talking about a very simple sum function, that is all. How can it be possible without trusting anyone, any single party, still we are able to compute the sum of n bit values? Looks like an impossible task, but we will do now some magic. We will see a very simple protocol for computing this sum function. Okay. So, now we do not make any assumption that we have a trusted third party. We will be designing a protocol according to which the parties will communicate messages among themselves, and we assume that to communicate parties have pairwise private channel. Okay. That means, there is a way for every party to communicate some message, whatever message it wants to communicate to any other receiver in a private, in a perfectly secure way. Okay. And we had seen in the last lecture how exactly such channels can be realized. The problem setting is the following: each party has a private bit bi, and the goal is to securely compute and announce the sum of n bit values, and it should be done in such a way that no party pi should learn anything beyond what it can learn from the final sum and its own input bit during the protocol execution. That means, whatever messages any party pi learns, gets during the protocol execution, that should be kind of independent of the inputs of the other parties. Okay. That is what roughly we want to achieve here. So, what will be the protocol? So, to begin with, it is easy to see that the final sum is in the range 0 to n. 0 because it could be the case that the inputs of all the parties is 0, n it could be the, because it could be the case that all the input parties have the bit 1. Okay. By the way, if all the parties have the input bit 1 and if the final sum is learnt is to be n, then anyhow parties will learn that all the parties have participated with input 1. That is not a breach of privacy, because that is allowed to be learnt. Remember, if the final sum is s, a final sum is n, everyone will know that okay, every party has participated with input 1, that is leaked anyhow from the input and the final output. That is not called a privacy leak or privacy breach here. In the same way, if the final sum turns out to be 0, fine, everyone will learn that every party participated in the protocol with input 0, that is not a privacy breach. But suppose if the sum is turned out to be say 1, then again the party whose input is 1, he will know that okay, I only have participated with input 1, but others have participated with 0, fine, that is again not a privacy breach. But suppose if sum is turned out to be 2 after the execution of the protocol, and suppose B1 is equal to 1, then party 1 will learn from this output that okay, definitely there is only one more party whose input is 1. Which party has participated with input 1? That should not be learned, because that is not allowed to be learned from B1 equal to 1 and S equal to 2. The information that is allowed to be learned from B1 equal to 1 and S equal to 2 is that there is another party and only one party who has participated with input 1, that is allowed to be learned. But anything additional apart from that, that should not be learnt in the protocol execution. Whereas, if B3 is equal to 0 and S equal to 2, from its viewpoint it will be learning that anyhow that there are two parties who have participated with input 1, that is allowed to be learnt from B3 equal to 0 and S equal to 2, but who are those two parties, that should not be leaked. So, that is what roughly I mean here, that nothing additional should be revealed beyond a party's own input and the function output. So, do not consider that if S is equal to n, then everyone learns that all the parties have participated with input 1 and that is a privacy breach. No, that is why I have stressed here the term anything beyond. Okay, right. So, since the sum is going to be a value in the range 0 to n, the parties will agree upon some public modulus capital M. Agree upon means they will, the protocol will be designed in such a way that all the operations will be performed modulo ZM, modulo M. That means, it will be ensured that all the values computed in the protocol, they lie in the range 0 to m minus 1 and m is strictly greater than n. Okay. That is what we mean by parties agree upon this public modulus. Now, here is the protocol. To start with, the first party, okay, it picks a random value, and since here n is equal to 4, okay, I am taking for demonstration purpose 4 parties here. That is why my sum value could be in the range 0 to 4, and that is why we have agreed upon the, we will be performing all the operations modulo 5, okay, and Z5 means the set 0, 1, 2, 3, 4. So, what P1 does is the following, it picks a random value k from this set Z5 with equal probability, it could be 0, 1, 2, 3, 4, and that is known only to P1. Now, it computes an encryption of its bit B1, and how it computes the encryption? It simply adds the value k to its bit, and that is the ciphertext C1, which it now communicates to the second party over the private channel, which is available between P1 and P2. So, people who are familiar with one time pad encryption, this C1 is nothing but OTP encryption of B1 with pad k. And remember, this plus operation is performed modulo 5, that means the value of C1 will remain in the range 0 to 4, because every time value crosses 5 we will perform value crosses 4 we will perform the mod operations. Okay. And P2 will know that okay, whatever value it is receiving, that is an OTP encryption of the bit B1, but since the pad k is uniformly random, it does not reveal anything about the actual value of the bit B1. Okay. Now, what P2 does? It takes the OTP encryption C1 and add its own input bit to that ciphertext. And if we expand the OTP ciphertext C1, the ciphertext C2, which now P2 is communicating to the next party, can be interpreted as if the sum of the first 2 bits B1 and B2 is encrypted using the pad k, and this ciphertext C2 is communicated over the private channel available between the second party and the third party. And now, the third party further extends this process. It takes the ciphertext which it is receiving and it adds its own input bit, and now this will be treated as an OTP encryption of the sum of the first 3 input bits using the pad k, and this will be communicated to the fourth party. And now, fourth party adds its own input bit, and this will be treated as if the sum of the 4 input bits is encrypted using the pad k, and this ciphertext or this encryption will be communicated back to the first party. Now, first party, if you see the value of C4 closely here, is getting an OTP encryption of the sum of 4 bits with respect to the pad k which is available with P1, So, it can just remove the pad k, or it can actually perform the decryption of your ciphertext C4. So, the decryption operation will be unmasking the pad. Unmasking the pad means subtracting out the pad. So, if the pad k is subtracted from this OTP encryption C4, that will give the sum S, namely the summation of B1, B2, B3, B4, which this first party can now announce to everyone publicly. That is a simple protocol. Now, we have to analyze this protocol and we have to argue that in this protocol any single party, we call it P1 or P2 or P3 or P4, any single party, does it learn anything beyond what it can learn from S and Bi, even if it is computationally unbounded. Let us make Pi computationally unbounded, that means even if the first party is computationally unbounded, does it learn anything about the inputs B2, B3, B4 beyond what it can learn about B2, B3, B4 from the sum and its own input value B1. That is what we want to argue. In the same way, we want to argue that suppose if P2 is computationally unbounded, after the protocol gets over, he will anyhow learn the sum, he has its own bit value B2. Now, it wants to analyze the messages that it has received during the execution of the protocol. Is it possible that if P2 is computationally unbounded, there is a mechanism for P2 to analyze the messages that it has received and infer anything additional about B1, B3, B4 beyond what it can infer from the final sum and B2 and so on. And we want to perform this analysis for every single party here. Okay. So, to prove the privacy property that indeed this simple protocol satisfies the privacy property, what we will do is the following. We will define first what we call as the view of any party Pi. Okay. So, I have written down the view of every party in this rectangular box, and roughly this is the information which is learnt by the party Pi during the protocol execution. So, the view will have definitely the inputs of the parties. So, sorry, I have not written it down explicitly here in the boxes. So, view will definitely have the inputs of the parties, and if there are any random coins which are used by the parties during the protocol execution, they also will be a part of the view. So, if you see here, no party except the first party tosses a random coin. It is only the first party who picks the random pad, but apart from that no party has any random coin being used in the protocol. So, k also will be a part of the view of the first party, and then whatever messages that party has received from other parties and communicated to the other parties, they will be a part of the view of that party. So, for instance, if I consider this party number 2, his view will be, it is learning the final sum, it would have received the ciphertext C1. So, that is why C1 is a part of its view, and it would have communicated C2 to the other party. So, that is why C2 is a part of its view, and B2 also will be a part of its view, because that is its own input. And to prove that indeed this protocol is secure, this simple toy MPC protocol is secure, we have to argue that Pi should not learn anything beyond what it can learn or compute itself from S and Bi, and this is equivalent to saying that anyhow the sum S will be learnt and Bi is available with the party Pi. Based on Bi and S, it can have multiple potential candidate values for the remaining parties, for the it will have multiple candidate values for the inputs of the remaining parties, which along with Bi would give the sum S, which is learnt by the party. We have to show that this view I, which is learnt by the party Pi during the protocol, that is equiprobable with respect to every such candidate B1, B2, Bi, Bn, which sums up to the given S. Okay. And remember here that the view V I here, then the view of the each party here, it is not a fixed set of values. That means, it is not the case that every time the protocol is executed, even with the same set of inputs B 1, B 2, B 3, B 4, the same ciphertext C 1, C 2, C 3, C 4 would be circulating in the system, because C 1 will be different every time, because the pad, one time pad is picked randomly in each execution. So, even if B 1 is same across multiple executions, C 1 will take different values, and if C 1 takes different values, C 2 will take different values, even if B 2 is fixed, and so on. So, that is why the contents of view I is not going to be a fixed set of contents, even if the inputs B 1, B 2, B 3, B 4 are fixed, and that is why view I here is a random variable, and it can take different values with different probability. We have to argue here for privacy that the probability distribution of view I is independent of the inputs of the other parties, namely you fix B I, you fix the sum S, then for every candidate remaining inputs, which along with this fixed B I gives you this fixed S, view I could occur with equal probability. And if we show this, then this is equivalent to showing that the information learnt by Pi is more or less equivalent to what Pi would have learnt in the ideal solution. Remember, in the ideal solution, the view of the ith party would have been just its own input and a function output, namely the sum S, because that is the only information learnt by Pi in that ideal solution. But in this toy MPC protocol, view I has other things as well, the ciphertext received by the party and the ciphertext which it communicates to the other party, and so on. If we show that view is distributed independent of the inputs of the other parties, then that is equivalent to showing that basically view I has the same amount or equivalent amount of information which Pi would have learnt in the ideal solution, and that is what we will do in our next lecture. Thank you.